Hi, I'm Janet Vorobyeva. This is my cathodic protection monitoring project for CSE 237D Embedded Systems Design. Corrosion is a problem. It affects all sorts of metal structures, and it can be costly and expensive. It takes your expensive and valuable infrastructure and turns it into useless rust. So mitigating corrosion is important and valuable. One way we can mitigate corrosion is you can take a reactive metal, like magnesium or zinc, and attach it to your main structure. Um, the reactive metal will corrode first, and it will protect your main structure from damage. This is called a cathodic protection system. Here's an example of a boat propeller with some zinc sacrificial anodes on it. You'll often find cathodic protection systems in places where metal is exposed to water, such as underground pipes, bridges, and hot water tanks in your home. Now, cathodic protection systems are very effective, but they have a finite lifespan. The sacrificial anode is consumed and has to be replaced every 5 to 15 years, depending on how the system is designed. This means you have to monitor it regularly. Typically, once a year, you're supposed to go and, send someone out with a multimeter to a cathodic protection test point and verify the health of the system. Unfortunately, in practice, this often doesn't happen. Which is a problem. These things won't get maintained and will fail earlier than they're supposed to. So my project for this quarter is to try to mitigate this by designing sensors to monitor cathodic protection systems. Now, the interesting thing about monitoring cathodic protection systems is they work by putting a positive charge on your structure, and you can actually harvest this electrical potential in a sensor. Now, there's not a lot of power available, hundreds of microwatts to milliwatts. But if you do an energy harvesting setup where you charge all day and send out a packet maybe once a day briefly, that's enough to power a sensor, which is good because you don't need any infrastructure or power to do this. So this isn't a new idea. I based a lot of my work off of a paper by a former student from my advisor's lab. This was a similar idea, but more of a prototype and sort of proof of concept, whereas for my project, I aimed to have something a little more integrated and to try to actually deploy it on campus. So my goals were I wanted to make a custom PCB design for this. It needed to be low power. I was aiming for a 150 microwatt power budget. I needed the sensor to send its measurements over LoRa radio, and then I needed a second gateway to receive those radio packets and forward them up to the internet. And I was originally planning to deploy this on campus. So, how did it go? I started by picking out the parts and designing schematics for the energy harvesting chip, microcontroller, and radio module. I integrated them into a custom PCB, ordered them, and assembled a PCB. Now, there were some issues where the JTAG header, which you use to program the board, I had accidentally swapped these two pins, which meant it didn't work. So I had to do some trace surgery on these very small traces, cutting here and here, and soldering two little wires to swap them, which I managed to do under a microscope, which was fun. But anyway, got that working. And then the board worked. I tested the power consumption and current draw of the board under a variety of circumstances, and I was able to get detailed measurements of the power consumption of the microcontroller and the radio, and was able to get them into their deepest sleep mode, so it was only consuming about 2.5 microamps when it was asleep. I also got the gateway working. This was kind of a hack-together thing, but I had a LoRa module and an ESP32 to connect to the Wi-Fi, and I was able to get it forwarding the packets. I had originally planned to deploy this in cathodic protection test points on campus, but that didn't end up working out, so I had to fall back to a magnesium rod in a steel bucket for my demo. But it worked well enough, and here's the demo. The board charges up off of the magnesium anode rod. It sends a packet over the radio. The gateway receives the radio packet, forwards it up over Wi-Fi into the cloud, and it shows up in a spreadsheet on my computer. That's my project. Thanks for listening.